Hey guys, so I've put together a proper screencast version of the session I gave on the slides I put together previously on non-parametric statistics. I'd originally written these a good number of years ago now, and over the years I kind of added to them and taken away. But I realised the quality of the last set of slides, especially when it got converted to the screencast, perhaps wasn't all that, and certainly the audio seemed to dip in and out of occasion. So consider this version 2. There's nothing different. I'm not going to say anything that's new or revelatory in comparison to the previous set, but hopefully we'll be able to sort of clarify things that might not have been clear from the previous screencast. So, as you can see from the image on the front here, there's a secret to non-parametric statistics, and it's all based on quite a brutally simplistic approach to how they deal with the data. And this is one of the great advantages that non-parametric statistics have, in that they make fewer assumptions about the quality, the properties or parameters of your data than parametric tests. Now, some books refer to them as being distribution-free tasks, and that's not quite true. For instance, if you have skew, then typically you might be wanting to find skewness present in each of your group's data. But the main point about this is because they have fewer assumptions about your data, they are more pliable, particularly in the instance of outliers, and they do not pose a problem for non-parametric statistics at all. Whereas obviously, as I'm going to demonstrate here, parametric tests would be particularly off-put by the presence of extremely high or low scores. Pardon me. Skip on to the next slide. So, again, as with all these sessions, the learning objectives, again, coupled with your own reading. Again, what we're going to look at today is the kind of general distinction between parametric and non-parametric inferential tests. So we're going to sort of make it clear as to when you should use a non-parametric test. We're going to analyze, or show you how to analyze data using 5 non-parametric tests, and these are the kind of the most common ones that you will come across. Certainly, when we do the inferential, the parametric tests in each of the sessions, the last statistic that we will do will be the non-parametric equivalent. So I'm not kind of just teaching you this as an aside. It is going to be a heads up to what we'll be doing in the main sessions as well. There are other non-parametric tests. There's numerous ones, but I'll be showing you 5 of the more kind of common ones that typically you might come across. So we'll look at how to interpret those and how you might sort of write them up in terms of a quick summary. Recommended reading, obviously a statistics book, the Dancian Reader, is particularly good if you're kind of new to statistics and you want someone to sort of give you like a guiding hand through how to sort of interpret and why you would actually do these tests in the first place. If you feel like you've got more of a robust understanding of statistics and you want to sort of dig that bit deeper, then any book by Andy Field, but particularly his Discovering Statistics, is a particularly a good read. It'll certainly help you uncover more about what the statistic is actually doing. Incidentally, both of these books use SPSS, which is the previous software that we used to use to analyze data. But as we've switched to Jamovi this year, you can still use both books. Many of the steps, the output is still going to look very, very similar, but just sort of bear that in mind. Okay, so to start off with, then, let's just roll back a second and think about our dependent variables. Well, variables in general. We might know that we say that they have different levels, or that they have different kind of properties, different kind of yeah, different parameters, different capabilities. And there was one theory put forward by Stevens which suggested you can separate out different types of variables by the degree of complexity that they have. So to begin with, let's say you have a variable that is a simple nominal variable. This just means that each of the levels, how you split up your nominal variable, is a discrete and simple category. So, for instance, you could think of political parties. You have separate discrete entities such as the Liberal Democrats, Labour, the Conservative Party, the Green Party, etc., etc. And they're all distinct and separate from each other. There's no, however you might think it's tempting to say, there is no kind of crossing of the boundaries from each other. There is no kind of midpoint, as it were. So all we can do here really is just, let's say we'd held an election or a quick vote in one of the classes. We could find out how many people voted Labour, how many people voted Liberal Democrats, etc., etc. All we can do is collect frequency data with this. We can't calculate means. If I told you, the mean political party was 2.54, what would that represent? It's a mishmash of things. It doesn't mean anything. So all we can do, because it is so simple, is just collect frequency data. The frequency counts that we are obtained in no way, shape or form say anything about whether one particular variable is better than another, is worth more somehow. It just represents, in this instance, who voted more for one party than others. If we did want to be able to sort of like rank the levels of a variable, the different type of outcomes, let's say, the different levels, then we would need to step up into a degree of complexity. And we can do this with ordinal level measures, which again kind of reflect discrete, simple categories. However, it is possible to rank these. So intuitively, they come in a particular order. So if you think of the outcome of a race, for instance, we know that whoever came first was better than whoever came second, then whoever came third and fourth, and so on and so on. If you think of test performance, people, if we use kind of categories, they could have, in terms of your master's degree, for instance, fails, pass, merits, and distinctions. And we know that one is better than the other. And so you think of questionnaire measures that use a Likert scale, which is something we'll talk more about in a future session. Then that is typically reflective of ordinal level variables. And just going back to the example of the race positions, we know that obviously someone who came first did better than someone who came in second place. But what we don't know is by how much better. We don't know if the kind of difference between the person who came in first and second was the same as the gap between the person that came in second and third. We simply don't know that. We only know, on a rather simple rule of thumb, that they perform better. If we wanted to, sort of be able to measure the difference in between those positions, as it were, what we need to do is step up into another level of complexity. And these are interval levels. And so you can think of a temperature scale. All the different kind of numbers on a temperature scale, be it Celsius, Fahrenheit, or centigrade. But each one of those has a set scale. So it goes up in sort of like 1 degree increments. And that difference is exactly the same up and down the scale throughout its entirety. So for instance, the difference between 22 degrees and 20 degrees, that kind of 2 degree difference is exactly the same as the difference between 65 and 63. It's the same scale up and down. But one of the kind of the drawbacks of an interval level measure is that there is no true zero. So if you think, for instance, of a temperature scale, 0 degrees doesn't mean that there's an absence of temperature. It's still an actual measure. There is some, temperature out there, but it doesn't reflect an absolute absence of that temperature. And so that's a drawback, because 0 doesn't mean 0. So if you think, if I gave you guys an IQ test and I made it devilishly complicated and you all scored 0 out of 10, does that mean that you have no IQ? No, you can't possibly mean that. All it would reflect is that you scored 0 on that particular test. But the 0 itself doesn't reflect an absence of a measurement. If we wanted that, we would need to have a ratio level measurement. And so this is where, for instance, if you think of something like reaction times that go from 0 milliseconds all the way up to, well, potentially infinity. 0 there means a genuine 0. If you think of measuring how much children have grown over the course of a 1 month period, then 0 millimeters would literally mean that that child has grown 0 amount. So there's an absence of growth, in other words. And because we've got that 0 there, that true 0, what we can do with the scales is have kind of ratio elements built into them. For instance, we know that, as I've got here, 800 milliseconds is twice as much as 400 milliseconds. We can't do that with interval measures. You can't say that 30 degrees outside is twice as warm as 15 degrees. It doesn't work on that same scale. Now, what's interesting to note, these kind of latter two levels, interval and ratio, for the purposes of most statistics, there's a negligible difference between them. Certainly, a lot of statistical packages, jamovi included, classes interval and ratio levels as the same. It just says that they are continuous data. Whereas nominal and ordinal, because they have different, quite distinct properties, they are treated separately. So whilst I've shown you kind of 4 here, in the kind of real world, then typically what you might find, you have nominal, ordinal, and continuous, which is what jamovi gives us. Parametric and non-parametric tests. As I said, there's a class of inferential statistics here where we want to find out whether things have happened by chance or not. But parametric tests, they rely on continuous data. So they're looking at interval and ratio level data. Strictly speaking, they shouldn't be looking at ordinal level data like you might get from questionnaires. But between me and the gatepost, quite often psychologists treat ordinal level data, questionnaire level data, as sufficiently robust so that, yes, they can measure it with parametric tests. But one of the kind of defining hallmarks is that the data that you obtain needs to be normally distributed. And the kind of statistics that are involved here rely on things like the mean, the average, the mean average, standard deviations, and measures of variance. And because of that, if you have any data that might have certain issues with these assumptions that have been made here, then that can potentially make parametric tests less reliable in their analyses. Non-parametrics, on the other hand, can be used to analyse both nominal and ordinal, but also interval and ratio data. It doesn't matter if it's normally distributed or not. Well, I say or not, if you look and read into more into this, you'll find out that some tests do need to have like similar levels of skewness across conditions and so on. But what's important is it doesn't matter if you've got outliers in there, maybe if you've got kind of bimodal distributions, because of what they do to the data, these non-parametric tests, that kind of strips away the kind of the problems that are inherent that face parametric tests. And just to sort of give an example of this, we've all got mobile phones. Excuse me. We've all got mobile phones, and let's say, you know, some people's are worth more than others. Some are kind of the latest iPhone 12s on a contract might be worth, you know, I don't know, £1,200 or something. Other people might have a cheap kind of, you know, pay as you go. Probably costs, you know, £20 down at the local petrol station. But let's just say, on average, people in any kind of like class of statistics, you might find that on average the mobile phone has a value of about £400, give or take. Obviously there'll be some above that and some below that, but on average, let's say £400 is the kind of the mean average value. Now, one of the problems about using the mean is if we happen to get some scores that are extremely outlandish. Take, for instance, if you do a Google search for the most expensive phone in the world, you'll find something that was kind of, you know, it's covered in diamonds, it's got platinum all around it, and it costs something like, I don't know, $2 million or something ridiculous like that. And let's say the owner of that phone came into one of our statistics sessions. So we just recalculated the mean to take into account of this new person. And we found out that the average mobile phone now, the mean average is £23,000. Well, you know, that doesn't reflect the value of that guy's phone. It doesn't reflect the true value of anyone's phone in the group. So in that case, the mean average isn't really representative of the kind of typical value of a phone in that group. The kind of the model that it's trying to put together to sort of explain the properties of or values of phones, it's pretty bust. It's just not worth it anymore. So if you've got a class of statistics that then rely on the mean and the kind of, you know, the standard deviations and then the variances as well, then they're all going to be way off base. And so in that instance, doing parametric analyses might not be the wisest case. Instead, what we could do, we could decide maybe, you know, we want to press ahead and I still want to do a parametric test. But what I could do perhaps is maybe, you know, remove that one person from my database. They're so unlike anyone else in the group that it's not really kind of a valid representation, so let's exclude them. But, you know, that might be a problem. Let's say you're working with, you know, hard to recruit clinical patients. You've only got a small number, let's say, you know, 12 participants taking part in a study. Can you really afford just to get rid of one of your patients just like that? Maybe instead you could do some sort of transformation where you change that person's score so that it still becomes, you know, the highest score, the highest value phone in your data. But some people might argue, well, you know, you're not really sort of giving a fair representation here. You're changing people's scores that they have genuinely obtained just to fit in with the vagaries of a particular statistical approach. And, you know, are you sort of like affecting the kind of quality or the complexity of the data by changing it in that type of format? Why don't you just use the non-parametric equivalent? And so that's something we're going to take a look at over the course of this semester. We've got a variety of different kind of scenarios in which it's possible to run statistical tests. So all these things here in this first column. And initially we've got, you know, a selection of the parametric tests that you can run, and then also what the non-parametric equivalent of those will be. So starting off, what we're looking at here is if we have nominal data and we're looking at the difference between kind of scores that we have obtained or that we've observed versus what we might ordinarily expect to obtain, then we would do something what's known as a chi-square. We don't teach you that on this course. It's a relatively straightforward analysis to do. You can't even do it by hand. But we've got quite a few things to get through, and because it's so simple and straightforward, what we tend to do is leave that to one side and concentrate on the other statistics anyway. You will do things like chi-square without realizing that you're doing it. For instance, the Shapiro-Wilk. When you run that to see if your analysis, if your data is significantly different from a normal distribution, that is based on the chi-square statistic. All you're doing is comparing data that you've got versus that which you might think you might expect to get. So what we're going to concentrate on is, as you can see in bold here, are these 5 parametric statistics here. And these are the equivalent of the parametric statistics that we're going to go through and teach you in the workshops. As I said before, at the end of each workshop, the final analysis that you'll do will be the non-parametric equivalent. So you'll be running it on exactly the same data, so you'll be able to see the kind of consistency in approaches and in the scores and the outcomes. Now, as I said, it's by no means an exhaustive list. There are plenty more non-parametric tests out there. Certainly, if you begin to read statistical journals, you'll find that there's many tests that aren't even widely known about or accepted. But in certain cases, people will use them. And so what we're going to just stick with is the far more common ones that you're more likely to come across when you pick up a paper. Obviously, if you find that you do have some tests that you aren't that familiar with, that isn't one of these 5, well, then what you can do is just exercise your independent learning and find out about it yourself. Okay, but one of the things a lot of students want to know is, how do I know which one to use? And this really is true of any statistical test. What you can do first of all is identify what's the design of my study. Is it between subjects? Is it within? Is it a mix? What about the level of the measurement? So think about the dependent variable. Is it nominal? Is it ordinal? Is it interval ratio, the kind of continuous measures? Because again, that might tell you something about your data. Go off and run and explore your descriptive statistics. We've already shown you how to visualize your outputs. This can give you an idea about your checking for assumptions. Can you see that normal distribution? Do you have outliers? Is there kind of elevated levels of skewness or kurtosis? Again, these are the type of things that can just help you identify whether your data might have some problems that can then sort of push you more towards the non-parametric approach. So, how do they do it then? What's the big secret about why non-parametric statistics don't seem to be as effective? Why they seem to be more robust than their parametric equivalent? As I said, it's a brutally simplistic approach, and kudos to whoever kind of thought of this. But all you do is take that raw data and convert it to an ordinal level. You just rank that data. So, as an illustration, if you think back to the Sydney Olympics that were held in 2000 or so, I've got here just some kind of made up data from the men's 100 meter freestyle swim. And I've got scores over here showing the times of the 8 swimmers that took part in one of the heats. And you can see, whoever came in first was had 22.83 seconds. Just behind him was someone 22.99, 23.14, and so on and so on. So all we do is simply rank these according to their order. So this is the raw score that we would have obtained, and we just rank them in ascending order so we know what position they came in. So we've converted the raw score to an ordinal rank. So I've got different screens here. So we've converted the raw scores to the actual rank, their position, as it were. Now, in this 2000 Sydney Olympics, I don't know if you remember, but there was one competitor, and he was given the nickname of Eric the Eel. He'd only learned to swim earlier that year, but through some kind of vagaries of qualification times and so on, he was able to represent his country at the Olympic Games in the 100 meters freestyle. And so this guy, he was very, very slow, obviously, because he simply wasn't used to swimming, and he was up against kind of Michael Phelps and that kind of crew. And so he, at the 50-meter mark, he turned in a time of 40.97 seconds. So you can see he was way behind everyone else. But what's important is that he came in 8th position. Now, just to sort of illustrate the kind of beauty of this kind of converting to ordinal ranks, it doesn't matter actually what time he got. Let's say he was even slower. He was over 2 minutes. What position would he come in? Well, he'd still come in 8th. He could have taken 4 days to swim that 100 meters, and he would have still come in 8th position. So you can see here, when we're dealing with non-parametric conditions, because we're not dealing with the absolute raw data anymore, all we do is convert it to these ranked, this ordinal level data, and then do the analysis on those ranks. So it doesn't matter whether you've got an outlier or not. That's still going to be, the 8th position or the highest score or whatever. But you only ever do the analyses on those ranks themselves, and that is the simplistic, the kind of exceptional brutality of the non-parametric statistics. Take the raw data, convert it into the ranked positions, and then do your analyses on those ranks. Whatever kind of pattern or trends that are in your data, in your raw data, are also going to be present in your ranked data. So it doesn't matter that you're not using the raw data anymore. Those kind of trends and differences, whatever, are still going to be present in your ranked data. Brilliant. So the first test statistic that we're going to look at out of those 5 is to do with correlation. Correlation is actually the first test statistic we're going to show you in this module, and we're looking at something called Spearman's rho. Now, Spearman's rho is just you're looking at how 2 variables might be associated with each other. And so we can take a look at any 2 variables, and we can plot them on something called a scatter plot. So we've got one variable here and a second variable here. So as scores increase on one variable, you might see that they increase on the second variable, with a line of data going from bottom left up to top right. And one of the kind of clear things that you can see with a Spearman's rho, or with an analysis in general, is even if you convert that pattern, you will still get to see, even if you still convert that to an ordinal level of data, you'll still see that pattern emerge. So, for instance, what I've got here is we're looking at people's anxiety levels, and let's say we're comparing how they scored on the state trait anxiety level, and also looked at Beck's anxiety inventory. So we've got 10 people. They've all been measured on 2 indices of anxiety. Well, you'd think if someone was high on one measure of anxiety, they'd also be high on the other one. It doesn't matter whether they have the same number of items or the same kind of response scale, how you answer the questionnaire. It doesn't matter. All we're looking at is the kind of the pattern of similarity between them. So that's what we've got here. Obviously these are the kind of the raw scores. And what we can do is, and again, this is what the statistic is doing behind the scenes. So you don't actually need to do this when you want to perform a Spearman's row. I'm just showing you, sort of like prizing back the software, what is actually happening. But all we do is, for the first measure, again, is just rank the scores. So you find out what was the lowest score on Beck's anxiety inventory. It was 31. And next was 32. So they get assigned a rank of 1 and 2 and 3 and 4 and so on and so on. And then you do that for the second level, the state trait anxiety inventory. So the lowest was 26, then it was 28, and so on and so on. So they get assigned a rank of 1, 2, 3, and so on and so on. And then all you do is perform the analysis. Well, rather, what Jamovi does is then perform an analysis on that data. And that's it. It's simple and as straightforward as that. When we teach you more about correlations in future, what you'll realize is at this point on, we do something called the Pearson's correlation, which is the parametric equivalent to the non-parametric Spearman's row. So again, to do this in Jamovi, what you would do is on the top menu, click on regression, and then you'll see you've got a variety of different tests, and we would just choose the correlation matrix. You see a variety of different options that kind of appear, but the ones that we're interested, you'll find Pearson's is selected by default, and so we'll just click Spearman's and it'll run the Spearman row analysis for us. Again, the output that we've got here in the table, this will show you the correlation, the degree of association between your variables. As you'll see in the session when we look at the correlation, this 0.07, that's going to be a number between -1 and 1. Obviously, the higher that it is, it kind of indicates it's a stronger correlation. And then we have the p-value underneath. So what's the likelihood if the null hypothesis was true and that there is no similarity between the state trait anxiety inventory and Beck's anxiety inventory? If that was true and there is no genuine relationship or overlap between those, what's the odds of getting our data from those 10 participants and having that correlation purely by chance? Well, according to that, it would be 31 times out of 1,000. So in other words, really sort of quite low. So it's highly likely that it happened by chance. So all we would do here is go back and then restate what we found in our study with the kind of statistical evidence underneath here. Again, indicating our correlation was 0.7, our p-value was 0.31, and that we had 10 participants take part in the study. Next up, we have the Wilcoxon signed ranks. And so this is the equivalent of something called paired t-tests. So this is where we have one group of participants on a repeated measures or within subjects design. And they get tested on 2 different conditions in a study. So let's say, for instance, as you can see here, let's say that we've got people who took part in some sort of stress management session. And what we've done, we've measured their stress levels before they took part in the intervention and immediately afterwards again. So what we're hoping to see is that there's a reduction in stress levels after they took part in the intervention. So again, we've got 10 people and we've got their pre and post, before and after scores. And what we do is, or rather, what the software does for us is find out the difference between those. So again, if it has worked, if it has reduced people's anxiety, or their stress levels I should say, then you'd find that you've got a difference here. Of course, you might get some people who, apparently based on their scores, had no reduction in stress levels, and so they would get a 0 here because they got the same before and after scores. You might even find you got some people who have an increase in stress, and their stress levels seem to get higher after having taken part in the intervention. And you can see there, obviously, 38 minus 40, that would give us a -2. So we can see that stands out there. So what Jamovi does for this statistic then, it takes those differences and it ranks them. So simply puts them in ascending order. So the lowest one, and it doesn't matter whether it's a positive or a negative, it's just the absolute value at this point. Now, if it's a 0, then because they are ties, they're not included in the analysis. So that's why I've written that they are omitted here. But the lowest score then was this 1. Okay. The next lowest was this 2. Again, forget whether it's positive or negative. We're just looking at the absolute value for now. The next lowest was 3, and so on and so on. So we build up a kind of like ranked order of these. Now you might notice that we've got 2 here that was 7. So we've got, well, that's kind of like, one of those was in 6th position, the other one was in 7th position. So all we do is kind of find the midpoint of 6 and 7 and call them both 6.5. No, 6.5th position, as it were. And if we want to, we can sort of like, find out the total of all those numbers. But what we're interested in now, again, because we've got different conditions in the study, when we have the raw data, what we're saying is that if we, even if we convert this to the ordinal, to the ranked data, we're still expecting to see the same pattern. We're still expecting to see scores to go down after having taken part in the intervention. And we can see that. If we just separate out whether scores kind of, increased after taking part in the intervention, as if there's one person there versus all the rest who had a decrease in their stress levels after having taken part in the study. So again, we can sort of look at the the totals of those if we just add them all up. So again, 34 out of the total 36 ranks here. So these 34, if you divide that by 36, then we're saying about 94% of results seem to sort of go in favour of the intervention, seem to suggest that it had a positive effect in reducing stress levels. Whereas 2 out of the 36 were in the unfavourable, so people's stress levels went higher. I'll come back to those in a second. So what we can do here is just put a circle around the highest total rank score that we've got, and that is our test statistic, our t-score. When we actually run the Wilcoxon signed ranks test in Jamovi, again, you'll be more familiar with this when we actually get round to looking at these type of analyses. You just click on the t-test and paired samples t-test, and one of the options that you get to choose is the Wilcoxon signed ranks test. So we'll do that, and again we're just going to be comparing the before and after scores. There's other kind of options that we can tick, but this is what we're concentrating on. And the output that we get. Remember, our test statistic was this 34, the highest sum of the ranks, and that's associated with a p-value of 0.03. So again, the idea that the null hypothesis, if it is true, what's the likelihood of our obtaining our pattern of scores, where 34 out of 36 ranks indicated that the stress levels had decreased after the intervention. Well, again, that's like 30 in 1,000 or 3 in 100. Highly unlikely. And what we've also got now, and this is a very, very recent addition to jamovi, is to be able to work out the effect size. And again, this is one thing that I've said, that the p-values only ever say whether your test statistic, the difference in scores, was significant. It says nothing about the actual size. But your effect size does do. So all it does, it compares the ratio of favourable to unfavourable results. So, I've said previously we had 34 out of 36 ranks were in the favourable position, i.e. stress levels reduced after the intervention. And so what we can do is just divide that. 34 divided by 36 gives us 0.944. Equally, we divide the 2 out of the 36 ranks and that were unfavourable, so stress levels got higher after the intervention, and that gives us 0.0556. So all we do is subtract one from the other, and that gives us kind of the ballpark figure of 0.89. So this is a number between 0 and 1. You can kind of think of it as a bit like a correlation, trying to interpret it in the same way. And so this indicates that yes, we have a significant result, but it's also quite a large difference between those pre and post interventions, of before and after scores. So again, as a suggestion to write this up, we could say there was a significant effect of the new stress reducing program upon stress scores. And again, I've got the statistical evidence here just to back that up, such that stress scores were lower after the program. And again, because we're reporting non-parametric statistics, then the convention is to report the median and IQR rather than the mean and standard deviations. Remember, we're not relying on mean and standard deviations for non-parametric analyses, because they wouldn't be a reliable indicator of what's actually being recorded. Truth be told, when it actually comes to it, these non-parametric statistics aren't relying on the median and IQR either, but they're a much kind of a closer approximation as to what it is that we're actually obtaining here. And we're finishing off just by saying that the size or the magnitude of that effect was large. Okay, so we've just shown you what to do if you've got one group tested twice. But what about if you've got two groups each tested once? So what we will use is something called the Mann-Whitney, or the Mann-Whitney-U test. And so again, what we've got here, just to illustrate what's happening, we're going to compare people who are left-handed versus right-handed. And what we're looking at is their ability to perform on a particular test of spatial ability. So we can see we've got the raw scores. Got the raw scores here for the left-handed people, and we've got the raw scores here for the right-handed people. Now, again, if we wanted to, we could just show the descriptives, so we can see that we seem to have a slightly different median average for left-handed and right-handed people. Now, the first step again is merely ranking your data, but in this case, rather than ranking per group as we did per condition in the Wilcoxon, what we're going to do here is rank all the scores across all participants. So from our two sets, our two groups worth of data, we find out whichever was the lowest score. In this case it's 47, and we give that person a score of 1. We then find the next lowest score, which is 55, and that person gets a 2. We then find the next lowest score, which is this person with 56, and they get a 3, and so on and so on and so on. Again, you can see if we're going to have a difference in scores between the median of our two groups based on raw scores, then pretty much once we convert those raw scores to these ranks, we would still expect to see that same pattern emerging in the ranked data. So again, we would continue with all the ranking, and you might find you've got two people from different groups who each have the same score. And again, that would be like, the 16th and the 17th person. So what we do is just find the midpoint of that, and then we assign a rank value of 16.5 to both of those people. So we can just continue with that and then work out the total of all of those ranks. And what you should start to see here, that this difference based on the raw scores is also manifesting itself, perhaps more so in fact, on these rank scores of each of those groups. This slide just explains all about the ranking, but we've already gone through that. Okay, so we've now got the ranks for our left-handed and our right-handed groups. Again, what the software does for us, it continues on to the next stage, and it calculates two values of U. And basically this U is a kind of factor of how many participants you've got in both of your groups by the total rank score of the first group. And it does that again for the second group as well. So you can see it's the same base set of scores, but we're just subtracting from that the total set of scores from the first group and from the second group. So from left-handed people and right-handed people. So you can go through and work out the equations here, and what we end up with is the U score. So again, we can see that for left-handed versus our right-handed groups. The smallest of those two values, this is what our test statistic would be, and that's what we would then, years ago you'd have looked that up in a table to find like a critical value for you. In other words, what 0.05 would be. Nowadays we just get the Jamovi software to do that for us, and it'll find out the precise p-value. So again, just to sort of explain what's happening here, 79.5 out of the total 100 ranks that exist in the data were in the favourable condition. So this gives us 79.5%. In other words, our group did as expected, whereas 20.5 were in the kind of the opposite direction. So again, you just do the division, and we're looking at those two type of ratios against each other when we're looking at the effect size. How to do the Mann-Whitney actually in Jamovi, same as before. You'll find out more about this when we actually do this type of test in the workshop. We'll look at the independent t-test, and what we can do is just select the Mann-Whitney at the bottom. Again, we've got the verbal ability score, or the spatial ability score it was, and we're going to compare our two groups on that, left versus right-handed people. And the output that we get from Jamovi is going to look something like this. So again, we've got the test statistic, which was the lowest of our two U values. And so what we can do is then find the probability of obtaining this kind of test statistic, this pattern of differences in our scores between left and right-handed people. If the null hypothesis was true and there was no genuine difference, then the likelihood of our obtaining that set of scores by chance is 0.028, 28 out of 1,000. That's very, very low. Again, it's below our cutoff of 0.05. Therefore, it's highly unlikely that it has happened by chance or by sampling error. And what we're trying to infer from this is that, in actual fact, it shows that maybe there is like a systematic difference between left and right-handed people in terms of their spatial ability. So, pardon me. To contextualize the effect size that I was talking about, again, what Jamovi does for the man-witty test is compute the rank by serial correlation. And we can see here is 0.59. Again, how this is calculated, what we do is compare the ranks that were favorable versus those that were unfavorable. So 79.5 divided by the 100 ranks gives us a value of 0.795. 20.5 divided by 100 is 0.205. You just do a subtraction between those two, and what we'll end up with is this 0.59. So this value between 0 and 1. Again, rule of thumb to interpret this, you've got the tables, I think on page 21 in your workbooks, which suggests that is a large effect size. So again, to write it up, remember we can just give a brief recap of the study, what the kind of design considerations were. We can use our descriptive statistics to pinpoint and identify an apparent difference in performance. So again, we can see here I've done that for left and right-handed people. Just to sort of throw things in a mix here, rather than reporting the median and IQR, I have reported the median and the range here. I've done this on purpose because you probably find some different textbooks or some different journals might report the median, others will report the median and IQR, others will do it with the range instead, or even sort of the minimum and maximum scores. Whatever you want, it's just an idea about how your scores vary around that. That's all. It gives you an idea about the kind of spread of scores. So again, that's what we're concluding, that left-handed people were found to be significantly better on measures of spatial ability than right-handed people. And again, I've got my statistical evidence here based from my analyses to report that. But I'm also sort of finishing off with the suggestion that the actual size of that difference was large. Okay, 3 down, 2 to go. What happens if, rather than if we've got one group who've been tested twice, like we did with the Wilcoxon, what happens if we have one group who've been tested 3 times? Well, I suppose technically we could go and do multiple Wilcoxon rank tests, but as you'll see in a forthcoming session, the more tests you do, that brings with it a whole host of other issues, of other problems. So rather than do that, what we can do is do what's kind of known as an omnibus test. And whether we've got 2, 3, 4, 5, 6, or hundreds of different kind of conditions, it is possible to test all of those in one go. And what we use for non-parametric data is something called Friedman's ANOVA. Now, I'm borrowing some data here from the Andy Field book. And Andy Field, again, fantastic. You really want to sort of get to know a statistic, and what it's done is he's broken down, what's actually happening with the test and how it's doing what it does do. But all we're doing is comparing one group that's been tested on 3 different conditions. So it's a within subjects or repeated measures design. So we're measuring people's weight as they are on a diet. So we can measure them at the start, at the onset. We can measure them 1 month in, and after 2 months we can see what their weight is. And again, just to sort of kind of illustrate what's going on, we could report something like the median and range values. So you would find here that weight seems to dip from the onset to the first month on the diet, but then people's weight seems to kind of spring back up, and the second month people weigh more than they did at the start of the study, which is quite a common finding. I'm sure many of you have experienced. So what do we do in this analysis then? Well, brace yourself. What happens is Jamovi, thankfully for us, what it does do, it begins to rank the data. Now, as what's happened with the Wilcoxon, what we do here is look at each person and we rank their scores in ascending order. So for this first person, we can see that their weight at the start was the lowest, so that gets given a rank of 1. Their weight on the second month was the second lowest. Sorry, their weight at month 1 was the second lowest, so we'll put that as a rank of 2. And then on month 2, it went up, and so we give that a rank of 3. Again, do that for all participants. Again, you'll notice some seemingly have it the opposite way around. This person, for instance, lost weight throughout the course, so his scores, his ranks are kind of the opposite direction. Some are a bit more kind of muddled. But again, what we can do at the end is just add up the ranks of each of those. Then what happens is that gets fed into this equation. So basically it's kind of producing a test statistic, this Friedman's ANOVA. It takes into account the kind of the number of participants that we've got as a factor of the kind of the total ranks, the total rank score under each of those different conditions. And you can sort of subtract from that a kind of multiple of the total number of participants that you've got. And what happens then in terms of running this analysis, again you'll see it's quite well labelled in Jamovi what you have to click in order to get this Friedman's ANOVA. So again, what we would do is have the data for our participants, their weight at the start, a month in, and on the second month. We compare them across those 3 months, and this is going to give us our Friedman's ANOVA. And essentially what this is going to be is the chi-square statistic. We have 2 degrees of freedom because we had 3 conditions overall. Therefore, if we're going to start comparing the conditions to the population, then one of those wouldn't be free to vary. So that only gives us 2 degrees of freedom. But what's important here, perhaps not surprisingly, based on the fact that the rank data that we've got a score of 19, 20 and 21, all very similar to each other. What we'd actually find then, we've got a p-value of 0.905. So if the null hypothesis was significant, if the null hypothesis was true, and there genuinely was a difference in people's weight on the length into the diet, then the odds of this happening by chance, it's like 905 out of 1,000. That's way above our 0.05 cutoff. So in other words, it's pretty likely this is all just happened purely by chance. There's nothing of interest, there's nothing of note happening here. Just got some random fluctuations of scores. That's why weight each time of month wasn't perfectly the same. It just happened by chance. So that's an example of a Friedman's ANOVA. So again, in terms of writing it up, exactly as he's done before, you talk about the weight of your participants at your 3 different time points. You maybe measure them in median and IQR or whatever, and then cite in the statistical evidence afterwards. Again, if let's just say that it happened to be significant, then what we could do is either do a selection of Wilcoxon's sign ranks tests to examine differences, or what you could do, sort of back in as an option for the Friedman's ANOVA, is just tick the post hoc measure, and this will do a series of tests for us where it will compare the 3 different conditions against each other, 1 versus 1. This is what's known as a Durbin conover in Jamovi. And again, we'll talk more about this in the actual session. So, fifth and final analysis then is called the Kruskal-Wallis. This is where we have multiple groups of different participants. So previously, when we looked at the Mann-Whitney, we had two groups, left-handed versus right-handed people. But what happens if we add in a third group, or a fourth group, or a fifth group of participants? Again, we can't just keep doing one group versus another and do lots and lots and lots of analyses. It's far better to do an omnibus test where we can test each different group kind of against each other in one big format. And how it does this, again, it looks at the ranks of the data across all participants. If there are differences in the raw scores between our different groups, then those same differences are going to manifest themselves when you look at the rank scores as well. So we'll do it across all 80 participants, and then we can begin to sift out what that looks like for each of the different groups. So the study that we've got from, again, borrowed it from the field. Andy Field has an amazing tendency to sort of bring up kind of examples involving sex and whatnot in his examples. Make of that what you will. But what we've got here is the effect of the amount of soya that people have in their diet. And when I say people, I mean men. And what effect that will have on their production of sperm. So you can see from the data here, he's got four groups. People who don't have any soya, who have 1 soya meal a week, 4 soya meals or 7 soya meals a week. And we have their sperm levels in terms of millions recorded for each participant in that group. So again, all we do across all 80 participants, we've got 20 participants per group here. We look at, what was the lowest level of sperm production in any participants. And it was this person here who recorded 0.31 billions. So he gets the lowest rank of 1. Person underneath just happens to be 2. You then find the next person, 0.33, who had a 3. And so on and so on and so on and so on. So you find out the ranks across all 80 participants. And what you can do is just sum those columns. So again, if we're expecting a difference in the kind of descriptive statistics here of our different groups based on raw scores, then that same difference, that same pattern is going to manifest itself in the rank scores of each of our groups. So again, you can see that those that have 7 soya meals in a week would seem to have the lowest sperm count, the ranks for the sperm counts from across the 4 different groups. Anyhow, once we've done all that ranking and we've got our total scores, it then gets entered into this equation, which is startlingly similar to what happened with the Friedman's ANOVA. So again, we sort of take into account the number of participants. We're looking at factoring in the total score of those ranks by how many people happen to be in that particular group, and then as a factor of that, the total number of participants that were in the study. So again, to do the Kruskal-Wallis, it's rather straightforward in Jamovi. You just find it from the menu. Again, all your variables that would appear in here, we would have our sperm count variable, our dependent variable here, and we're going to compare each of our 4 groups across doing that. If this happens to be significant, what we could do is just tick this box here to run different kind of pairwise comparisons. This just means we can compare every single group against every other group. So we've done that, and the output looks something like this. So again, it's based on a chi-square, and it suggests that again we've got 3 degrees of freedom because we have 4 different groups here. and therefore we lose one of those groups. So we've got 3 kind of group scores that are free to vary to get the same as what occurs in the population. But the likelihood of our getting that kind of pattern of scores, this kind of test statistic, is, again, it's below our cutoff of 0.05. So in other words, we've got a chance of what? 34 in 1,000. It's unlikely to have happened by chance. There's the suggestion that maybe, increasing levels of soya perhaps might affect diet. We don't know that for sure. Certainly the ANOVA, Kruskal-Wallis, indicates that there's a difference here between our 4 groups, but we don't know where that difference lies particularly. Whether it's, it's the 7 meals of soya are significantly better than or worse than the others. What we do need to look at are the post-hoc tests. And this just, compares each and every single group against all the other groups. So we've got no soya meals. We look at their sperm levels against those that had 1 soya meal, against 4 soya meals, 7 soya meals, and we find out whether or not there are any significant differences here. In fact, once we do all those kind of comparisons and we get the test statistic, what we can look at is the p-value here. And you probably find that we only have these 3 groups here that show a significant difference. So this is between no soya meals and 7 soya meals, between 1 soya meal and 7 soya meals, and 4 soya meals and 7 soya meals. So in other words, what we're saying here is that it's the group that have 7 soya meals, they have a significantly lower level of sperm than any other group, whether they had none, 1 or 4 soya meals in a week. So again, that's just an indication of how you would run and interpret those analyses. So again, in terms of the write-up, again, give a recap of the design, talk about the median and the range, or the IQR values, and then we have, the kind of the statistical evidence here to kind of back that up. Again, you'll be at a p-value of 0.034. That's below our cutoff of 0.05, indicating that the null hypothesis may be false. Could be making a mistake. We don't know that for definite, but chances are, the likelihood is that this hasn't happened by chance. And so because that was saying that there's a difference across our 4 groups, what we then did is a series of pairwise comparisons. And this was just, every group against every other group. And what we found is that it was only the group that had 7 soya meals. Whenever you compare them to the other groups, they have significantly lower levels of sperm. Whew. Okay, that's it. That's the end of this kind of, I'd like to say, a whistle-stop tour of non-parametric statistics, but we're like an hour and 10 minutes into this. But just to kind of summarize, then, obviously, if your data doesn't meet the assumptions for analyzing with a parametric test, a lot of people seem to think, oh God, I'm going to have to play around with it, do some kind of tortuous analysis or something, or change my data, play around with it, exclude participants, try and alter the data to make it fit. And why bother doing that? Why sort of think that's it? All bets are off. When what you can do is actually just do the non-parametric equivalent. It makes perfect sense to me. And yet quite often what you tend to find, much as I've done here, ironically enough, is that the non-parametric tests in any kind of statistics book quite often get relegated to the last chapter. They're all kind of lumped together under one chapter, almost like it's the poor relation of the family or something. And that definitely needn't be the case. You shouldn't think of them as last resort, but as a viable alternative. One kind of drawback, I suppose. And you'll see this in each of the sessions where we run a parametric analysis on the data, and then we finish off running a non-parametric analysis. What you'll find is that the non-parametric equivalent tends to be less powerful. So in other words, if a genuine significant result does exist, then with a non-parametric test, then you're less likely to be able to detect that than the equivalent parametric test. However, that's if you're doing this on kind of your normally distributed data. But if your data has got problems, then your parametric test is kind of, all over the place. It might not be as robust as you think it is, and might give you kind of slightly different or inaccurate results. And so in that case, it's perhaps better being running the non-parametric equivalent anyway. You can even run both and see, do they still give you the same answer, the same kind of ballpark figures, which would be a great thing to do. It kind of shows that you're kind of flexible, you're aware of both approaches, and so I'd certainly advocate something like that. So just to finish off with then, again, think of these not as an inferior bunch of tools of statistics that we just don't talk about. A genuine, legitimate suite of analyses. You'll find them reported in many journal papers. And what we've done here is just give you an introduction as to what's actually happening, how they run. And in the actual workshops themselves, you'll see that we will do these, and hopefully you'll find them much more straightforward to run with. Okay, cheers guys, that is it.